Quantum physics is a strange thing. At least, it's strange for us. Because the rules of the quantum world governing how this world works at the level of atoms and elementary particles, governing the behavior of light and matter, as Richard Feynman formulated it, do not coincide with the rules familiar to us. The rules of what we call common sense. Quantum rules seem to tell us that a certain cat can be alive and dead at the same time, and a particle can be in two places at once. Moreover, they say that any particle is also a wave. And everything in the quantum world can be described exclusively in terms of waves, or exclusively in terms of particles, if you prefer there. Erwin Schrödinger found the equations describing the quantum world of waves. Werner Heisenberg equations describing the quantum world of particles. And Paul Dirac proved that these two versions of reality are exactly equivalent to each other and describe the same quantum world. All this was clear by the end of the 1920s. But to the great disappointment of many physicists, not to mention ordinary mortals, no one either then or later could offer a reasonable explanation from the point of view of common sense. Of course, you can just ignore this problem in the hope that someday it will disappear by itself. The equations in the version that you prefer work fine. If you need, for example, to design a laser, explain the structure of DNA or build a quantum computer, and so it was, generations of students have received no instructions other than to shut up and count. That is, do not ask what these equations mean, but simply substitute numbers in them. This roughly corresponds to the instruction to plug your ears with your fingers and hum at the same time la la la, I can't hear you. More thoughtful physicists still seek solace and peace. They have already offered quite a few more or less desperate means to explain what is happening in the quantum world. These means, quanta of consolation, are called interpretations. At the level of equations, none of these interpretations has an advantage over the others, although the interpreters themselves and their followers, of course, will tell you that the light of true faith is carried by their favorite interpretation, and those who adhere to other creeds are heretics. On the other hand, mathematically, none of the interpretations is in any way inferior to the others. Most likely, this means that we are missing something serious. Someday, perhaps, a magnificent new description of the world will be discovered, capable of making all the same predictions as modern quantum theory, but at the same time meaningful. At least, one can hope for it. In the meantime, perhaps it's worth offering you a critical overview of the main interpretations of quantum physics. They are all insane from the point of view of common sense, and some of them are crazier than others. But in the quantum world, crazy doesn't necessarily mean wrong, and being crazier than the rest doesn't necessarily mean being even more wrong. I chose 6 examples, the traditional half-dozen. Mainly in order to justify the use of a quote from Alice Through the Looking Glass as an epigraph. I have my own opinion about their relative merits, but I will try to keep it to give you the opportunity to make your own choice. And if you want, you can just plug your ears and sing la la la, I can't hear you. However, before offering you these interpretations, I must explain at least briefly what exactly we are trying to interpret. Science often advances by leaps and bounds. As they say, 1 step forward, 2 on the spot. But in this case, it seems to make sense to start with 2 steps forward, thereby making another curtsy in the direction of Charles Lutwidge Dodgson, better known as Lewis Carroll. The whole strangeness of the quantum world is revealed in what we usually call the two-slit experiment. Richard Feynman, who received the Nobel Prize for his contribution to quantum physics, preferred to call it the two-hole experiment and said that this phenomenon was completely, absolutely impossible to explain in a classical way. This phenomenon is the very essence of quantum mechanics. But in fact, it hides a single secret and contains the main features of all quantum mechanics. A surprise for those who remember from the school physics course that with the help of this experiment it is proved that light is a kind of waveform. The school version of the experiment features a dark room in which light falls on a simple screen, a sheet of cardboard or paper. It has two tiny holes or, in some versions, two narrow parallel slits. Behind this screen there is a second screen, already without any holes. The light, passing through two holes in the first screen, falls on the second screen, where it forms a kind of pattern of light and shadow. The way the light diverges from the holes is called diffraction, and the pattern is an interference pattern, because it arises as a result of the interaction of the interference of two beams of light emanating from two holes. And this pattern exactly corresponds to the pattern that would have to occur if the light moved as a kind of wave. In some places, the waves add up and create a bright spot on the second screen. In others, the crest of one wave falls on the trough of another. They compensate for each other and leave a dark spot. An interference pattern of exactly the same type can be seen in waves that will disperse on the calm surface of a pond if two pebbles are thrown into it at the same time. One of the characteristic features of such interference is that the brightest light spot on the second screen is not directly behind one of the holes, but exactly in the middle between them. Where one would expect complete darkness on the second screen, if the light were a stream of particles. Yes, if light were a stream of particles, one would expect that a bright spot would form behind each hole, and darkness between them. So far, so good. The experiment proves that light moves like a wave, as Thomas Young guessed at the beginning of the 19th century. Unfortunately, at the beginning of the 20th century, another experiment clearly showed that light behaves like a stream of particles. The experiment consisted in the fact that electrons were knocked out of a metal surface by a beam of light. This is called the photoelectric effect. When the energy of the knocked-out electrons was measured, it turned out that the energy of each electron is always the same for light of any given shade. Bright light knocks out more electrons from the surface, but nevertheless they all have the same energy. And exactly the same as the energy of a smaller number of electrons knocked out by dimmed light. The explanation for this phenomenon was given by none other than Albert Einstein. Through particles of light, which we now call photons, and he himself called light quanta. The amount of energy a photon carries depends on the color, and for any given shade, all photons have the same energy. As Einstein wrote, the simplest concept is that one quantum of light transfers all its energy entirely to one electron. The amplification of light simply increases the number of photons, quanta of light with the same energy that each of them can transfer to an electron. It was for this work, and not at all for the theory of relativity, that Einstein was awarded the Nobel Prize. For a century, light has been perceived as a wave. Now physicists had to start perceiving it as a particle. But in this case, how to explain the experiment with two holes? It gets worse. Seeing that experiments with the photoelectric effect cast doubt on the wave nature of light, in the 1920s, physicists became even more confused. They learned that an electron, an archetypal particle of the subatomic world, can behave like a wave. The experimenters directed electron beams onto thin gold foil sheets from 1/10,000th to 100,000th of a millimeter thick and observed, on the other side of the leaves, what would come of it. Studies have shown that electron beams, passing through the gaps between atoms in the atomic lattice of a metal, are scattered in exactly the same way as light is scattered in an experiment with two holes. George Thomson, who conducted these experiments, was awarded the Nobel Prize for proving the wave nature of the electron. His father, Joseph John Thomson, received the Nobel Prize for proving that electrons are particles, and lived to see the day when the prize was awarded to George. At the same time, both awards were well-deserved, and nothing could more clearly demonstrate the strangeness of the quantum world. But that's not all. The riddle of wave-particle dualism, as it began to be called, since the 1920s, lay at the center of theoretical discussions about the meaning of quantum mechanics. Much of the theorizing about the fundamentals of quantum mechanics gave physicists solace, which I will talk about later. But the mystery itself in all its splendor was brought to the fore in a series of beautiful experiments begun in the 1970s. So I will skip half a century of searching for solace and introduce you to the modern facts concerning this main mystery. If you find it difficult to accept the following statement, remember that, as Mark Twain said, the truth is more improbable than fiction, because fiction must remain within the limits of plausibility, and the truth is not. In 1974, three Italian physicists Pier Giorgio Merli, Gianfranco Messaroli and Giulio Pozzi developed a method for observing a process equivalent to an experiment with two holes for electrons. Instead of a beam of light, they used a beam of electrons flying out from the filament. The beam was passed through a device called an electronic biprism. The electrons enter the biprism through a single entrance and meet an electric field there, which splits the beam in two. Half of the electrons are sent out through one outlet, the other half through the second. As a result, they end up on a detector screen similar to a computer screen, where the impact of each electron leaves a white dot. These dots remain visible on the screen for a while. So as the number of electrons that have passed through the experimental setup increases, an ordered picture is formed on the screen. When one electron is sent into the biprism, it flies out of one or another exit with a 50-50 probability and leaves a dot on the screen. If a beam of electrons passes through the installation, they leave a lot of overlapping points on the screen, which form a pattern, an interference pattern characteristic of waves. That in itself didn't mean anything. Even if electrons are particles, there are a lot of them in the beam, and passing through the installation, they could well interact and form an interference pattern. After all, waves on the water surface also form interference patterns. And water consists of molecules that can be considered as particles. However, that wasn't all. The Italian experiment was so precise that the electrons could be released one by one, like planes on departure from a busy airport. And like departing planes, the electrons flew one after the other with a significant interval. The distance from the electron source, it was arranged a little more cleverly than a simple filament, to the detector screen was 10 meters. And the next electron left the source only after its predecessor reached its destination. I hope you have already guessed what happened, and 1,000 electrons were fired one after another to form a pattern on the screen. An interference pattern appeared on it. And if we assume that individual particles, in order to form this picture, acted together like interacting water molecules in a pond, then the interaction between them should occur not only through space, but also through time. Such an experiment became known as double-slit diffraction of a single electron. If the electrons are fired one at a time, as in a two-slit experiment with light, each of them will leave a speck of light on the detector screen. Over time, the specks accumulate and form an interference pattern, as if the electrons were waves. The Italian team published their amazing results in 1976, but it did not raise a wave in the world of science. At that time, few researchers cared about how quantum mechanics worked. The main thing is that it works. That is, so that the equation can be used for calculations and correct prediction of experimental results. And how exactly an electron or a beam of electrons gets from point A to point B does not matter for an engineer designing, say, a TV. You can draw an analogy with that disappearing breed of racing drivers who do not care at all what happens under the hood of their cars. They just sweep around the track round and round at high speed. The only advice that, not without irony, was given by teachers to students who still wanted to figure out why the equations of quantum mechanics work, was the advice I already mentioned to shut up and count. That is, to use equations and not think about what it all means. In the 1980s, this position began to raise more and more questions. Not least because of new discoveries. When a group of Japanese scientists led by Akira Tanimura conducted a series of similar experiments using new technical capabilities, their results, published in 1989, made a lot more noise. In the 2002 year, readers of the Physicist World magazine called the experiment on double-slit electron diffraction the most beautiful physical experiment. There was one detail that did not suit scientists. In the experiments with electronic bow prism, there was no physical barrier similar to the first screen in the classic double-slit experiment with light. Both paths through the installation, both channels have always been open. And in the 28th year, Pazzi, with another group of colleagues, took the next step. Scientists conducted an experiment in which electrons were shot one by one through two real full-sized physical slits in a thin screen and recorded from the other side of it in the usual way. As expected, the electrons entering the detector formed an interference pattern. When the Italian team closed one gap and conducted the experiment again, there was no interference pattern. Instead, a simple light spot was formed on the detector screen, located directly behind the slit. Exactly what one would expect from a particle stream. But how can an individual electron, alone passing through a hole in the wall, know whether there is another hole nearby through which it could in principle pass, and whether it is open or closed in order to change its trajectory accordingly? The next step was obvious in theory, but incredibly difficult to implement in practice. It was necessary to build an installation with two holes in the nanoscale, which can be opened or closed while the electron is still flying. Is it possible to trick the electrons by changing the configuration of the installation after they have started on their way? This difficult task was undertaken by a group of scientists from the USA under the leadership of a Dutch-born Herman Battelen. The researchers published the results in the 2013 year. I described their experiment in the essay Quantum Riddle, published for Keitel. Since it contains exact numbers, I cannot improve this description and will give it here in its entirety. The experimenters made two slots in a gold-coated silicone membrane. The thickness, or better to say, the thickness of the membrane was only 100 nanometers. The thickness of the gold coating is 2 nanometers. The width of each slot was 62 nanometers, the length was 4 micrometers. A nanometer is 1/1000th of a meter, a micrometer is 1/100000th. These parallel slots were located at a distance of 272 nanometers from each other. The distance was measured from the center of one slot to the center of the other. The device had a fundamentally important addition. An automatic mechanism with a piezoelectric drive could move a tiny flap along the membrane, blocking one or another slot with its help. During the experiment, 1 electron per second flew through the installation, and the formation of each picture on the screen took 2 hours. The process was recorded on video. In a related series of runs, the research team observed what happens when both slots are open, when one of them is closed, and when the flap is moved to block the other slot. When both slots were open, the pattern forming on the screen, as expected, was an interference pattern. But in both cases, when only one of the slots remained, nothing of the kind was observed. Again, the electrons knew how many slots were open. To top off the rest of the riddles, revealed or, perhaps it would be better to say, confirmed by the experiments of Italian and Japanese scientists. Each electron seemed to know not only the configuration of the experimental setup at the moment of its passage through it, but also what happened to the electrons that flew before it and those that would fly later. Richard Feynman predicted this phenomenon half a century before the events described. Based on what scientists knew about the behavior of light by that time, and on the discovery of electronic waves, he set up a two-slit experiment with electronic ones in his imagination. In lectures on physics, Feynman described a thought experiment that you should not try to carry out in reality, because in order to demonstrate the effects that we are interested in, the installation for it would have to be done on an impossibly small scale. What was impossible in 1965 turned out to be possible in 2013. This would certainly have pleased Feynman, who, among other things, was keenly interested in nanotechnology. As Batalin and his colleagues announced, they managed to fully implement Feynman's thought experiment. Their experiment has indeed exposed the central mystery of the quantum world. The very essence of quantum physics, one single secret. But no one knows how the world can be so arranged. Before moving on, it is important to learn one more lesson from the experiment with two holes. It's not just that electrons and similar objects behave like waves and particles at the same time. It seems that they pass through the installation as waves, and they reach the detector screen as particles. Sometimes they behave as if they were waves, sometimes as if they were particles. This clarification is as if it is very important here. There is no way we can know what quantum objects really are, because we ourselves are not quantum objects. We can draw analogies with what we know from experience, and these are waves and particles. This was pointed out by physicist Arthur Eddington in a very interesting manner back in 1929. In his book The Nature of the Physical World, he wrote, "No familiar concepts can be woven around an electron. Something unknown to us is doing something incomprehensible." Such a formulation does not particularly resemble a coherent theory. I've read something like this somewhere before. I think it sounded like this: sticky sharkies were stabbing at nova. Perhaps it would really be better for us to think about the flimsy balls that poked around the nova in the experiment with two holes than about electrons that behave like waves and like particles. In order not to clutter up the presentation, I will not always preface with a reservation, as if you are the events or objects of the quantum world that are being discussed. Consider that it is in the right place. Indeed, dusting might turn out to be a better term than the one commonly used to refer to one fundamental quantum property of electrons and other particles. As a rule, it is called spin or, simply put, rotation. Of course, spin is a cozy familiar concept, the same as a wave or particle, and just as much deceptive. On the one hand, the equations tell us that any quantum object must turn twice to return to its original position, whatever it means in the physical sense. I am definitely not able to imagine this event. But spin is useful properties when discussing many quantum phenomena, since it can take two values. They can be represented as directed up and down and denoted as positive and negative spin. This simplifies the consideration of many issues, which otherwise could be enormously complicated. Take, for example, probability. In the context of quantum mechanics, the idea of probability was introduced on a solid mathematical basis by the German physicist Max Born. Without delving into mathematics, we can assess the importance of this idea by the example of spin electrons or the stabbing of Sharkov, as Eddington might prefer to say. Using the equations of quantum mechanics, one can describe a thought experiment in which an atom emits an electron flying into space. In reality, this is a process called beta decay. An electron has a spin, positive or negative. It is impossible to determine this in advance. The odds are 50-50. After conducting the experiment 1,000 times or simultaneously with thousands of atoms, we will count 500 electrons, perhaps a little more or a little less with a positive spin and 500 with a negative spin. You can catch a single electron and measure its spin. Up to this point, it is impossible to say what this spin will turn out to be. So far, nothing surprising. But Einstein realized that the equations of quantum theory predict something amazing when it comes to two electrons flying in opposite directions. In certain circumstances, the conservation law applies here, according to which these electrons must have opposite spins. One positive, the other negative. As a result, they compensate each other. However, the equations show. When electrons fly out of an atom, they don't have a definite spin. They are in a so-called superposition, a mixture of positive spin and negative spin states. The electron decides which state to accept only when it interacts with something else. Einstein pointed out the following. If two electrons must always have opposite spins, then at the moment when the first electron decides that its spin will have a positive value, the second electron must acquire a negative spin, no matter how far apart they are. Einstein called it a terrible long-range operation, because at first glance it seemed that the electrons must maintain a connection with each other at superluminal speed, which excludes the special theory of relativity. Boris Podolsky and Nathan Rosen were able to develop Einstein's idea and present it in the form of an article. It was published in 1933. Some, however, believe that the co-authors hindered rather than helped Einstein, since the article was written poorly, with unclear wording. According to the initials of the authors, it is known as the EPR article, and its central idea as the EPR paradox, although this is not a paradox at all, but just a baffling question. In 1935, introducing another famous paradox, Schrödinger named a way by which two quantum systems are connected by a terrible long-range action, entanglement. The EPR article stated that quantum theory makes the reality of the properties of the second system dependent on the measurement process performed on the first system, although this process does not affect the second system in any way. No reasonable definition of reality should, it would seem, allow this. The authors came to the conclusion, we are forced to conclude that the quantum mechanical description of physical reality is not complete. Einstein believed that there must be some fundamental mechanism known as hidden variables. Thanks to him, the electrons, flying in different directions from the source, are deprived of the opportunity to choose the value of the spin, positive or negative. Everything is already predetermined. The release of the EPR article caused fierce controversy among experts, but the real breakthrough in understanding entanglement and its consequences occurred only 3 decades later, and largely because one of the most prominent mathematicians of his time, John von Neumann, made a mistake in an important book on quantum mechanics, which was published in 1932, before the publication of the EPR article. In this book, von Neumann presented evidence that theories with hidden changes are not able to explain the behavior of the quantum world, that such theories are impossible. His scientific authority was so high that everyone believed him without checking the mathematical calculations. More precisely, almost everything. A young German researcher, Greta Hermann, discovered an error in his reasoning and wrote about it in 1935. In a philosophical journal that physicists haven't read. Experts discovered this publication much later. In the second consolation, I will tell you that this error did not completely stop the work on impossible theories with hidden variables. But it wasn't until the mid-1960s that a physicist analyzed von Neumann's arguments in detail and showed what was wrong with them. The resurrection of hidden variables might not have pleased Einstein, since the same physicist proved that all such theories should include the same creepy long-range action that Einstein really disliked and which in more formal language is called non-locality. This physicist was John Bell, who, after taking a vacation at CERN, the European Organization for Nuclear Research, went to the United States for a few months to work on something that would seem interesting to him. The 2 articles resulting from this break in daily work have changed the well-known facts about the quantum world more significantly than anything else since the discovery of wave-particle dualism. First, Bell explained what was wrong with von Neumann's reasoning. Then he showed how it would be possible, in principle, to design an experiment that would test the existence of non-locality effects. More precisely, this experiment would allow us to test the assumption of local reality. The definition of local here suggests that there is no creepy long-range action. Objects affect other objects only in their location, determined by the distance that light can travel in a certain time. Reality is a concept according to which the real world exists regardless of whether someone is looking at it or not, whether someone is measuring it or not. Due to the probabilistic nature of the quantum world, Belli's proposed experiment would require measuring a large number of pairs of particles, such as electrons or photons, passing through the setup. This hypothetical experiment was designed so that after a large number of runs, two sets of measurements should have been obtained. If one set of numbers turned out to be larger than the other, it would prove that the assumption of local reality is valid. This relation is known as Bell's inequality, and the related set of ideas is known as Bell's theorem. If, contrary to Bell's inequality, another set of numbers turned out to be larger, it would mean that the hypothesis of local reality is not true. If quantum mechanics is correct, Bell's inequality must be violated. Either the world is real, but with a terrible long-range effect in it, or it is locality, but on the condition that nothing is real if no one is watching it. Physicists have tried this path before, although many of them did not even realize it. When Robert Hooke and Isaac Newton developed their ideas about gravity in the 17th century, they realized that the moon was held in orbit around the Earth by some force that attracted them to each other, and that the planets were held in their orbits around the sun by the same force. Hooke and Newton understood that they were talking about action at a distance, and did not describe this long-range action as creepy. They had no idea how it worked. That is why Newton answered such questions with the famous Latin phrase hypothesis non fin. I'm not making up hypotheses, which meant you might as well be guessing how gravity works as I am. The effect of gravity at a distance baffled him, just as quantum long-range action baffles us. In the 20th century, Einstein, having developed the general theory of relativity, replaced the idea of the action of gravity at a distance with the idea of the curvature of fabric, space, which is caused by the presence of matter, although it must be admitted that this idea still seems creepy to some. Perhaps some future Einstein will someday replace the creepy quantum long-range with some less creepy idea. In any case, experiments have already proved that this phenomenon itself is real. To carry out the experiment proposed by Bell, technical solutions were required that were not available in the mid-1960s. And the physicists did not expect to see it delivered. However, these experiments were carried out by the beginning of the 1980s using photons instead of electrons. As a result, it was proved that Bell's inequality is violated. Since then, this has been confirmed by many similar experiments on an increasingly sophisticated technical base. Local reality is not a reliable description of our world. John Bell himself said at a conference in Geneva in 1990, "I am not aware of any concept of locality that works with quantum mechanics. Therefore, I think that we are doomed to non-locality." Einstein may have believed that no reasonable definition of reality could allow this. But we are forced to conclude that reality, in his own words, is not reasonable. However, the most impressive feature is often overlooked. Although the starting point for Bell's theorem was an attempt to understand quantum physics, and the words quoted earlier were said at a conference on quantum physics, the results relate not only to the field of this science. They relate to the whole world, to our universe. It doesn't matter if you think that one day quantum physics as a description of our world can be replaced by something else or not. Experiments show that local reality is inapplicable to the universe. Whether you prefer to console yourself, preserve reality and accept non-locality, or preserve locality and reject reality is a matter of your personal preferences, as we will see later. But it is impossible to preserve both. Although, in principle, it would be possible to refuse both at once, if you really want to damage the brain. However, before seeking solace for our boiling brains, it is perhaps worth bringing the history of entanglement to our days, since many serious practical applications follow from it. These include, in particular, quantum teleportation. This phenomenon is based on the experimentally proven fact that if two quantum objects, for example, two photons, are entangled, then no matter how far apart they are, what happens to one of them will necessarily affect the other. In essence, they are separate parts of a single quantum object. Quantum teleportation cannot be used to transmit information faster than the speed of light, because probability and randomness are involved in what happens to each particle. If one photon is transferred to some random quantum state, then the second one will simultaneously assume another quantum state. But sometimes an observer near the second photon will see only a random change of state, obeying the rules of probability. In order for this change to transmit some information, whoever caused the change in the state of the first photon, whoever it was, must send messages to the observer in traditional ways slower than the speed of light and tell him what is happening. But if one photon is affected in a certain way, the second photon can be turned into an exact copy of the first. Sometimes it is called a clone, while the state of the first photon is randomized. In fact, it turns out that the first photon was teleported to the location where the second one was. But since the state of the first photon will be lost in this case, it is impossible to call this process duplication. And again, to complete it, it is also necessary to send information to the observer through some kind of pre-light communication. Teleportation allows you to transmit information, but requires both a quantum communication channel and a classical channel. Huge efforts of scientists were directed to the creation of such systems. First of all, because such technology promises in the future the creation of fundamentally unbreakable ciphers necessary for both business and government. Any attempt to listen to the quantum channel would cause distortion of the transmitted data, making them useless and revealing the very fact of interference. And it doesn't matter if someone manages to listen to the traditional channel. According to experts in quantum cryptography, its contents can be published in newspapers or posted on social networks for all interested parties. Both channels are required to read encrypted information. In addition, entanglement plays an important role in the development of quantum computers, and this topic is of great interest these days. Researchers dream of a completely secure quantum internet in which quantum computing, entanglement and teleportation will ensure absolutely secure transmission of information. Experiments of this kind have already gone beyond the walls of the laboratory into the big world and even beyond. In the year 2012, a group of Chinese scientists teleported quantum information across Qinghai Lake at a distance of 97 kilometers. In the same year, a group of European scientists teleported photons 143 kilometers between the islands of Palma and Tenerife in the Canary Archipelago. Both experiments, we note in parentheses, confirmed the violation of Bell's inequality. This fact is now taken for granted by physicists as much as the fact that apples fall from trees to the ground. The experiment on the Canary Islands involved ground stations in the mountains at an altitude of about 2,400 meters above sea level, where thin air significantly reduces atmospheric interference. Above, the air is even more rarefied, and at an altitude of less than 143 kilometers above the island of Palma, the boundary of space begins. In the 2016 year, China put into orbit the Moji satellite, named after an ancient Chinese philosopher, from which entangled pairs of photons were sent to two stations located high in the mountains of Tibet at a distance of 1,200 kilometers from each other. And although the satellite was moving at a speed close to 8 kilometers per second, the photon beams were directed exactly at the target. The behavior of photons followed Bella's theorem, which surprised no one, but in fact it was a genuine triumph of modern technology. Such equipment works only at night, because sunlight blinds the detectors, and only 1 out of every 6 million photons sent from a satellite can be captured on Earth. Fortunately, photons are now inexpensive. Nevertheless, there are already plans to create a constellation of satellites with more powerful photon sources that could be captured even during the day, which would become the basis for a quantum communication network, as well as for teleporting Earth's photons to a satellite. Probably, by the time you hear this, there will already be new successes in this field, and new scientific news headlines. But if techies can continue to follow the shut up and count rule, then physicists can't come to an agreement among themselves about what all this means. Why is the world the way it is? It's time to take a closer look at several areas in which scientists are looking for solace. But let's go back to Earth and recall the experiment with 2 holes, in which each electron seems to know how many holes are open at that moment and where it is going. Maybe even here the matter is not complete without confusion. The notorious creepy long-range action. If a pair of photons flying in opposite directions is essentially part of a single quantum system, then is it possible to consider the entire setup of a 2-slit experiment and an electron, or all electrons as parts of a single quantum system? Maybe the electron knows which holes are open, because the state of the holes is also part of the state of the electron. However, the very concept of entanglement was still unknown when physicists first tried to find solace in one of the interpretations of quantum mechanics, which for several decades became generally accepted. The interpretation of quantum mechanics, which has become the defining point of view of physicists for several decades, is based on the idea of waves and largely on a departure from the as-if clause. In the 1920s, physicists already knew that the quantum world could be described using one of 2 mathematical methods. The first of them, which found its expression in the Schrödinger equation, considered wave interactions. The second method, which operated exclusively with numbers in the form of matrix tables, was based on the works of Werner Heisenberg and Paul Dirac. Both methods gave the same answers, and which one to use was a matter of taste and personal choice. Since most physicists were already familiar with wave equations, they were mostly chosen. However, in any quantum calculations, the relations between the 2 states of the system are calculated. In this case, the system can be an electron, an experiment with 2 holes, or, in principle, the entire universe, as well as any intermediate variant between an electron and the universe. If you have a set of parameters describing a system in state A, you can calculate the probability that after some time this system will be in state B, but at the same time you have no information about what happens between these 2 moments. An archetypal example is an electron in an atom. In some cases, it is possible to make calculations as if. Again, this reservation, the electrons were in circular orbits corresponding to different energy values. If an atom emits energy in the form of light, some electron disappears from one orbit and appears on another, closer to the nucleus of the atom. If an atom absorbs light, the electron disappears from its orbit and appears on atoms more distant from the nucleus. In this case, the electron does not move from one orbit to another. One minute he was here, and the next he was there. This phenomenon is known as a quantum leap. According to Schrödinger's calculations, the wave theory was supposed to explain what happens in the process of such a jump. But it failed, and the researcher said, "If these damn quantum jumps stay with us forever, I'll probably regret that I ever got involved with quantum theory." Well, it remains only to sympathize with the famous physicist. Quantum jumps have not gone away and will not go away. The matrix approach is more honest. It does not promise to explain to us what happens in the interval between states A and B, but it is less comforting than the Schrödinger equation. This view of the quantum world, adopted for several decades, is known as the Copenhagen interpretation of quantum mechanics, since Niels Bohr lived in this city. The name, coined by Werner Heisenberg, caused serious irritation to Max Born. He was not part of the Bohr group and did not work in Copenhagen. However, his idea of quantum probability became part of this interpretation. However, in the late 1920s, Niels Bohr dominated discussions about quantum physics. And it wasn't limited to the name. Bohr spread the alternative, quite viable interpretation so much that it was almost forgotten for 2 decades. A little later I will present this theory as a second consolation. Bohr was a pragmatist, willing to put together a working theory from scraps of various ideas without worrying too much about what it all meant. As a result, we simply do not have a clear and definite formulation of the Copenhagen interpretation. Although Bohr was very close to announcing it at a conference in Coma in 1927, long before the Copenhagen interpretation acquired a name. The Coma conference was a turning point in the history of physics. It was there that physicists got acquainted with the tools necessary to shut up and count, applying quantum mechanics to solving practical problems involving atoms and molecules, for example, in the field of chemistry, lasers and molecular biology, and without thinking about the fundamental basis and meaning of phenomena. Bohr's pragmatic approach extended to his interpretation. He said that we don't know anything except the results of experiments, and the results depend on what we actually want to measure. That is, from the questions that we consider it necessary to ask the quantum world of nature. However, these questions are colored by the experience of our everyday existence on a scale much larger than the scale of atoms and other quantum objects. We can assume that electrons are particles and construct an experiment to test this hypothesis by measuring the momentum of an electron. In this case, we imagine the electron in the form of a tiny billiard ball. We take measurements and, well, wow, we do it, which confirms the hypothesis that an electron is a particle. But let's say that one of our friends, who believes that an electron is a wave, prepared an experiment to measure the length of this wave and, wow, she succeeded. Which confirms the idea of the wave nature of the electron. So what? The set responds. From the fact that an electron behaves as if it were a particle when you are looking for particles, and as if it were a wave when you are looking for waves, it does not follow that it is actually one or the other, much less both at the same time. What you look at, you get. And what you're looking at depends on what you decide to look for. According to the Copenhagen interpretation, it is pointless to ask what quantum objects, such as electrons and atoms, are and what they do when no one measures them or looks at them, if you prefer. While everything is logical, there is nothing to worry about. But boron quickly leads us into muddy waters. This is where probability comes into play. Schrödinger, when proposing his wave equation, considered it a literal description of an electron or other quantum object. Just an electron is the simplest example. It is convenient to use it as an illustration. For him, the electron was really a wave. However, having accepted the baton from Schrödinger, Bohr rushed in the other direction. He combined the Schrödinger wave equation with Max Born's ideas about quantum probability. It turned out to be a very strange, even a little frightening mixture, which worked and still works when it comes to quantum calculations. But as soon as you stop thinking about it, your head immediately starts to hurt. In this new picture, the equation derived by Schrödinger is proposed to be considered as a probability wave, and the chance of detecting an electron at a particular point is determined by the square of the wave function. To do this, the equation describing the wave as such, in fact, multiplies itself at each point. When we measure or observe a quantum object, the wave function collapses into a point determined by probabilities. And although some locations are more likely than others, in principle, an electron could appear at any point of those at which the wave function propagates. Here is one very simple example that will emphasize the strangeness of this behavior. Imagine a single electron locked in a box. The probability wave propagates so that it fills this box evenly. And this means that the chances of detecting an electron at any point inside the box are exactly the same. Divide the box in half with a partition. Common sense tells us that now the electron should be in one of the halves of the box. But the Copenhagen interpretation of chi states that the probability wave still fills both halves of the box, and an electron is equally likely to be detected on either side of the partition. Now we cut the box along the center of the partition and get two boxes. We'll leave one in the lab, and put the other in a rocket and send it to Mars. According to Bohr, we will still have an equal 50-50 chance of detecting an electron in a box in the laboratory or in the same box on Mars. Now let's open the box left in the laboratory. We will either find an electron in it, or not, but the wave function will collapse anyway. If the box in the laboratory is empty, the electron is on Mars. If an electron is detected, then the box on Mars is empty. This is not the same as saying that our electron has always been either in that half of the box or in this one. The Copenhagen interpretation insists that collapse occurs only when the contents of the box are checked in the laboratory. This is the essence of the idea behind the EPR paradox and the famous Schlesinger riddle about a cat, alive and dead at the same time. But before delving into this story, I want to see how the Copenhagen interpretation explains the experiment with two holes. According to the Copenhagen interpretation, which was taught to me when I was a student and is still taught to too many as the only way to understand quantum mechanics, an electron is emitted from some source, an electron gun. On the one hand, experimental installations are like particles, and immediately dissolves into a wave of probability, which spreads through the installation and is directed to the detector screen from its other side. This wave passes through all the open holes, interfering with itself or not, as it turns out, and when it reaches the detector, it is displayed as a pattern of probabilities that is distributed across the screen. At this moment, the wave collapses and turns back into a particle, whose position on the screen is determined randomly, but in accordance with these probabilities. This is called collapse, the collapse of the wave function. The electron travels as a wave, but it stays in place as particles. The wave, however, carries with it not only probabilities. If a quantum object has a choice in which state to stay, for example, an electron can have a positive or negative spin. Both of these states are somehow included in its wave function. This situation is called a superposition of states. And the state in which a quantum object eventually turns out to be at the moment of its detection or interaction with another object is also determined at the moment of collapse of the wave function. In 1955, while giving a lecture at St. Andrews University, Werner Heisenberg believed that the transition from the possible to the actual occurs during the act of observation. This method is quite suitable for calculating quantum behavior. It's as if electrons and similar objects will actually behave that way. At the same time, the method raises many difficult questions. One of them is found in the so-called delayed choice experiment, invented by physicist John Wheeler. He began with the fact that photons that are fired one at a time in an experiment with two holes still form an interference pattern on the detector screen. But according to the Copenhagen interpretation, if a device is placed between the screen with holes and the detector screen that will track exactly which hole the next photon passed through, the interference pattern will disappear, thereby demonstrating that each photon actually passed through only one hole. They talk about delayed selection because we can make a decision whether to observe photons or not after they pass through a screen with two holes. Of course, human reactions are too slow for this, but such experiments were carried out using automatic devices that turned on or off the monitors after the photons passed through the screen with holes. Experiments show that the interference pattern really disappears when photons are observed. This means that each photon or the corresponding probability wave passes through only one hole, despite the fact that the decision to observe this photon is made after it has passed the screen with holes. Wheeler suggested imagining a similar experiment on a cosmic scale. A well-known phenomenon of gravitational lensing. Light from a distant object, such as a quasar, is focused by the gravity of an intermediate object, say, a galaxy, and bypasses this kind of gravitational lens in two or more ways. As a result, a double image of the object appears in the detectors here on Earth. In principle, instead of obtaining two images, it would be possible to mix light that has passed through different paths and obtain an interference pattern of waves that have bypassed the gravitational lens along different trajectories, a kind of cosmic version of the experiment with two holes. But we can observe photons before they form an interference pattern, and track exactly which way they passed around the lens. Then, judging by the results of laboratory experiments, the interference pattern should disappear. Let's say a quasar is 10 billion light-years away from us, and a galaxy playing the role of a gravitational lens is 5 billion light-years away. According to the results of already known experiments, what these photons did billions of years ago and billions of light-years from here is affected by what we decide to measure here and now. What's going on anyway? As Wheeler himself put it, the Copenhagen interpretation tells us not to ask such questions. She's not that great, then. In essence, the Copenhagen interpretation asserts that a quantum object does not possess a certain property. No property until it is measured. This raises a lot of questions about what constitutes a dimension. Does the human mind have to participate in it? Is the moon in place when no one is looking at it? Does the universe exist just because human beings are intelligent enough to notice it? Or the interaction of a quantum object with a detector can also be considered a measurement. And where exactly in the gap between these two extremes are the boundaries between the quantum world and the classical world of the good old Newtonian physics? Schrödinger was guided by similar considerations, offering his famous riddle about a cat locked in a room. He used the German word for a room, not a box. With a hellish machine that can kill a cat, but is in an equally probable 50-50 superposition of states. Complementing this example, imagine that a detector in a room measures the spin of a particular electron. If it turns out to be positive, the device will work and the cat will die. If negative, the cat is not in danger. The electron is in a superposition of states before the measurement, but there is no one in the room who can see what happens when the detector is turned on. Will the wave function collapse or not? Or the cat will also be in a superposition of states. At the same time, the dead are alive until someone opens the door and looks into the room. In my continuation of this idea, there are two more offspring of the famous cat, believing that he survived, whom I call Schrödinger kittens. These identical twin cats, the daughters of Schrödinger's cat, live in identical space capsules, where they have everything necessary for life, even toys. The capsules are connected by a tube, in the middle of which there is a box with a single electron. The wave of this electron fills the box evenly. At some point, a partition is lowered in the box, dividing it, as well as the capsules, into two parts. Each of them communicates with a box containing half a wave of electrons. After that, the capsules are sent at the same speed in opposite directions until they are at a distance of a couple of light-years from each other. Each capsule has a detector that registers the presence of electrons. After some time, the device that is not necessarily the same in both cases will open a half box in each capsule. If there is an electron there, then the adult cat will already die. If not, he will live. But there is no intelligent observer who can understand what is happening. And what, will both cats end up in a superposition as a result of all these actions? Now imagine that some intelligent alien in a passing ship catches one of the capsules and looks inside, seeing a cat there, alive or dead. Is it really at this moment that the wave function in each of the capsules will collapse? And what the alien sees will determine the fate of the second cat at a distance of 2 light-years from the first. Yes, if you believe the not-so-beautiful Copenhagen interpretation. Are there any alternatives? There are many of them, although they may seem as ridiculous as the Copenhagen interpretation itself. First, let's consider the one that originated simultaneously with Copenhagen, was almost crushed by boron in infancy, but survived and continues to fight. Louis de Broglie tried to solve the riddle of wave-particle dualism in a different way. He didn't say that an object like an electron can be a wave or a particle, depending on how you look at it. He did not say that an electron is a wave and a particle at the same time. He suggested that there might be two separate objects. Some kind of wave and some kind of particle, and they jointly generate the effects that we observe in experiments. De Broglie was one of the pioneers of the idea of waves in quantum mechanics. He was the first to suggest that if, as Einstein established, something previously considered a wave, light, can be considered in the same way as particles, photons, then objects previously considered particles, electrons, should be considered as waves. This assumption was soon confirmed experimentally and led Schrödinger to create his wave equation. For de Broglie, deep reflections on the meaning of wave-particle dualism were natural. He proposed his own solution to the riddle at the same conference in Como, where Bohr outlined the basics of the Copenhagen interpretation. In many ways, de Broglie's pilot wave theory is the most natural and obvious way to explain wave-particle dualism. De Broglie suggested that the wave and the particle are real, and that the wave, called the pilot wave, leads the particle to its destination, as an ocean wave carries a surfer to the shore. In an experiment with 2 holes, the pilot wave propagates through both holes and interferes with itself, forming a pattern of interacting waves. Particles passing through the experimental setup start at slightly different speeds or in slightly different directions. Therefore, they move in slightly different directions, following the waves and forming an interference pattern on the detector screen. We measure the properties of particles, but the properties of the wave are not available to us. We can only guess about its existence by the behavior of particles hidden from us until the moment of detection. This approach became known as the theory of hidden variables. A well-shuffled deck of cards can serve as a useful analogy for us. Imagine a deck of cards so tiny that they obey the laws of quantum physics. Let's put the deck face down in a microscopic device that allows you to open the cards by turning them over one by one. Hidden variable theories say that when the top card is opened, its suit and dignity are randomly selected from 52 possible options available in the deck. With a 50-50 probability you will get a card of the red suit, with a 1 in 52 probability a 5 of clubs, and so on. Until you look at the card, its merits and suit are hidden. But in fact, this card has always been exactly this suit and this dignity, even when you weren't looking at it. In this sense, it is not a real variable. Having opened the first card, let's assume it really was the Trev 5, we have 0 probability of seeing the Trev 5 next time. The probability is 26 to 51 to see a red card and so on. Compare this with the Copenhagen interpretation, which states that a card has neither suit nor dignity until you look at it. It is the act of viewing that makes her choose her suit and dignity from the available options. But in both cases, if you continue to open the cards, you will see approximately the same random sequence determined by probabilities. For example, you will never see the 5 of clubs twice. The experiment does not distinguish between interpretations, but in explaining what forms this sequence, the difference will be huge. David Lindley draws an analogy with a golfer practicing on a lawn with a hole. He carries out a series of strokes on the ball, aiming at the same hole, but the ball rolls each time with a slightly different speed and in a slightly different direction. Because the technique of hitting a golfer inevitably has small variations, and the surface of the lawn is not perfectly smooth. As a result, each time the balls roll in a slightly different direction and overcome a slightly different distance. After the athlete made 100 strokes, the swords rolled across the lawn and formed a pattern defined by the irregularities of the surface. But the final position of each ball can in principle be determined if you know the exact shape of the surface, as well as the exact speed and direction of the initial movement of the ball. In this sense, the interpretation of the pilot wave is deterministic and eliminates the element of randomness associated with the collapse of the wave function. And at the same time, the collapse of the wave function as such. Every particle at every moment of time has well-defined properties. Just like with a well-shuffled deck, we won't know what these properties are until we look. At the conference in Coma, de Broglie outlined the arguments related to the pilot wave in detail, not limiting himself, as I am now, to general reasoning. Looking back from a height after knowledge, John Bell in 1987 wrote in his book What Can and Cannot Be Said in Quantum Mechanics. This idea seems so natural and simple and allows us to solve the dilemma of the particle wave in such a clear and simple way that it is a huge mystery to me why everyone ignored it so amicably. In fact, this is not such a big mystery. First, I have already mentioned that Bohr, with the help and assistance of Wolfgang Paul, poured contempt on this idea and crushed de Broglie's theory rather by the strength of his personality and the weight of his scientific reputation than by the persuasiveness of his arguments. But reputation is not everything. The second reason why the idea of good or together with other theories with hidden changes was trampled into the mud was von Neumann's erroneous proof that such theories are impossible. De Broglie gave up trying to promote his idea, and it was firmly forgotten by physicists. When the American David Bohm put forward a similar idea in the early 1950s, he knew nothing about his predecessor. At first, this led to tension between him and de Broglie, who was offended that he was not mentioned. However, later everything smoothed out, and now the idea of the pilot wave is often called the de Broglie-Bohm interpretation. Today it is especially interesting how Bohm came to his version of the pilot wave. As a young researcher, Bohm wrote a textbook on quantum physics, which was published at the beginning of 1951. It set out the Copenhagen interpretation so well that the textbook was approved even by Paula, who was known for harsh criticism of all those whom he considered intellectually inferior to himself. That is, everyone in general. Einstein also acknowledged that Bohm explained the Copenhagen interpretation in the best possible way, but he contacted Bohm and stressed that, in his opinion, the Copenhagen interpretation is wrong. Bohm decided to see if there was no other way to explain what was happening in the quantum world. And soon I discovered that there is such a way. His pilot wave model was mathematically equivalent to the Copenhagen interpretation and gave the same answers to quantum questions. Basically it was the same model as de Broglie's. But Bohm went a little further in describing the interaction between the quantum and classical world. However, his theory was based on hidden variables, and von Neumann said that this was impossible. Not least for this reason, and also, at least in the USA, because during the Makar witch hunt Bohm was branded as a communist sympathizer, many physicists did not take Bohm seriously. If von Neumann said that this is impossible, then there must be a mistake somewhere in the Boa model. There was, however, one very significant exception. In 1952, John Bell worked at the British Atomic Energy Research Centre in Malvern, in Leicestershire. As one of the best young scientists, he was granted a year's sabbatical to conduct research. Bell went to the University of Birmingham, where he studied quantum theory and learned about the idea of the Bohm pilot wave. Bell immediately formed an opinion different from that of most physicists. If Bohm's idea works and von Neumann claimed that such ideas are impossible, it should follow that it was von Neumann who was wrong. Unfortunately, at that time von Neumann's book was published only in German, which Bell did not speak. He returned to his main work on designing particle accelerators, and in 1960 he moved to CERN. In 1963, when von Neumann's book was published in English, Bell found an error in the author and outlined his conclusions during a sabbatical in the United States. Bell also proposed his own version of the theory with hidden variables as an additional proof of von Neumann's error. But, as I mentioned, he showed that all theories of hidden variables, including the pilot wave theory, are not local. In one of the articles published during his trip to the USA, Bell wrote, "It is the requirements of locality, or, more precisely, the requirements that the result of measurements of one system does not depend on the operation on some other distant system with which the first system interacted in the past, generates the main difficulty in such issues as the mystery of EPR or, say, my example with kittens in space, where, according to the theory of Dobro or Boa, the electron is always in one half of the box and there is no superposition. In the interpretation with a pilot wave, it is clearly required that at any moment properties such as the speed of one particle or how it changes direction of motion depend on the properties at the same moment of all other particles with which this particle interacted earlier." I have never seen such a comparison in others. But it reminds me personally of the so-called Mach principle. Physicist Ernst Mach, who had a considerable influence on Einstein, drew general attention to a mystery that had been troubling scientists since at least the time of Newton. This mystery is related to inertia. If you push something, that something resists the attempt to set it in motion. I am not talking about friction, because we are talking about an imaginary situation where an object floats freely in space. He will remain at rest or continue to move in a straight line. Robert Hooke was the first to point out this possibility until he is pushed. When pushed, the object will change its speed, direction of movement, or both. But how does he know that he is changing direction or speed? In relation to what is the change measured? One does not need to observe and reflect too much to notice that inertia is a resistance to a change in motion in relation to the universe as a whole. To see this mystery in all its glory, you do not need to be transported into space in your thoughts. Even Isaac Newton, in his great book The Beginning, described an experiment with a bucket that you can do at home. Newton hung a bucket of water by the handle on a long rope. He twisted the rope well and let it go. The bucket began to unwind, but at first the water level in it remained the same. The fact that the bucket was moving in relation to the water did not affect her behavior in any way. Then, when the water picked up the rotation, its level dropped slightly in the center of the bucket, forming a concave surface. Newton grabbed the bucket by the sides. It stopped spinning, but the water inside continued to move for some time, and its surface remained concave, gradually flattening as the rotation slowed down. The shape of the water surface depended on how it moved relative to some mysterious fixed frame of reference, and had nothing to do with how the water moved relative to the bucket. Nowadays, this frame of reference is defined as the average distribution of masses in the universe. You don't even need a bucket to see the effect of the universe on local objects. It is enough to observe the surface of tea or coffee in a cup when you stir sugar in it. So it is the average distribution of masses in the universe that forms the frame of reference by which such changes are measured. Somehow, a local object is influenced by everything that is outside of it. The Mach principle states that the inertia of a particle is due to some interaction of this particle with all other objects in the universe. But what kind of interaction it is has been a mystery for a long time. It is possible that its solution is an interpretation with a pilot wave plus not locality. This leads to an interesting conclusion that appears in another interpretation. The third consolation. The interpretation with the de Broglie or Boma pilot wave refers to the entire universe. The behavior of a single particle here and now depends on the position of all other particles in the universe at this moment. The consequence of this conclusion, however, is better discussed in the context of our third consolation, a multi-world interpretation. But before proceeding to it, it is necessary to mention one amazing comment on Bohm's theory made by a person from whom one could rather expect support. Einstein, who in fact initiated Bohm's attempt to find an alternative to the Copenhagen interpretation, wrote to Max Born on May 12, 1952. Have you seen how Bohm, and indeed de Broglie, believes 25 years ago that quantum theory can be interpreted differently by a determinist? This, in my opinion, is cheap reasoning. No one can say exactly what Einstein meant. But his comment once again highlights the confusion caused by all interpretations of quantum mechanics without exception. If you have heard about the multi-world interpretation of and, then you probably believe that it was put forward by the American Hugh Everett in the mid-1950s. In a sense, this is true. Everett really came up with this idea entirely on his own. But he did not know that 5 years before him, the same idea had essentially occurred to Erwin Schrödinger. Everett's version is more mathematical, Schrödinger's is more philosophical. But the main thing is that both authors wanted to get rid of the idea of the collapse of the wave function, and both of them succeeded. Schrödinger willingly told anyone who was willing to listen that the equations, including his famous wave equation, say nothing about collapse. Bohr screwed this thing to the theory to explain why we see only one result of the experiment, a dead or a living cat, and not a mixture, not a superposition of these states. But from the fact that we register only one outcome, one solution of the wave function, it does not necessarily follow that there are no alternative solutions. In an article published in 1952, Schrödinger pointed out the absurdity of expecting some kind of quantum superposition to collapse just because we look at it. Obviously, it is absurd, he wrote, that the wave function should be controlled in two completely different ways, sometimes by the wave equation, but sometimes by the direct intervention of an observer independent of the wave equation. Although Schrödinger himself did not apply this idea to his famous cat, it easily solves this riddle. Having refined Schrödinger's terminology, we can say that there are two parallel universes, two worlds, and in one of them the cat remains alive, and in the other it dies. When a box is opened in one universe, a dead cat is found in it. In another universe, the cat in the box turns out to be alive. There have always been two universes, they were just identical until the moment when the infernal machine decided the fate of cats. There is no collapse of the wave function. In 1952 in Dublin, Schrödinger, anticipating the reaction of colleagues, stressed that although his equation describes, as it seems, different possible options, these options are not alternatives, in fact they all occur simultaneously. He added, almost any result announced by a quantum theorist is associated with the probability of this or that event, and there are usually a great many alternatives. The idea that this is possible, not alternative options, and all this is actually happening at the same time, seems delusional and simply impossible. The theorist believes that if the laws of nature took this form, well, say, for a quarter of an hour, then we would see how the world around us is rapidly turning into a quagmire, into a shapeless jelly or plasma. All the outlines are blurring, and we ourselves are probably turning into jellyfish. It's strange that he believes that. As far as I understand, he is sure that unobservable nature behaves exactly this way, according to the wave equation. The previously mentioned alternatives come into play only when we make an observation. And it certainly doesn't have to be scientific. Nevertheless, it seems that, according to the quantum theorist, nature keeps only our perception and observation of it from rapidly turning into jelly. A very strange thought. No one reacted to Schrödinger's idea. It was ignored and forgotten, considering it impossible, and Everett developed his own version of the multi-world interpretation on his own, only to have his idea ignored almost as unanimously. But it was Everett who suggested that the universe splits into different variants with each act of quantum choice, which muddied the waters for a decade ahead. Everett expressed this idea in 1955, while working on a dissertation at Princeton. In its draft version, he used a comparison with a dividing amoeba that splits into two daughter cells. If the protozoa possessed intelligence, an absolutely identical history would be preserved in the memory of each daughter amoeba until the moment of separation, and then their own personal history would begin to accumulate. By analogy with Schrödinger's cat, before the infernal machine is triggered, there is one universe and one code. Then two universes, each with its own cat, and so on. Everett's supervisor, John Wheeler, advised him to work out a mathematical description of the idea for a dissertation and for an article published in the Review of Modern Physics in 1957. But at the same time, the analogy with the amoeba disappeared somewhere and appeared in print much later. However, Everett pointed out that although no observer will ever feel the existence of other worlds, the statement that they cannot exist because we do not see them is no more convincing than the statement that the Earth cannot revolve around the Sun because we do not feel its movement. Everett himself never tried to promote the idea of a multi-world interpretation. Even before defending his dissertation, he began working for the Pentagon in the Weapons Systems Assessment Group. He had to deal with the application of mathematical methods in the documents they were innocently called game theory to the problems of the Cold War. Some of his works have not been declassified to this day. In fact, he disappeared from the field of view of the academic community. It was only at the end of the 1960s that the idea of Everett gained some fame. When it was accepted and enthusiastically promoted by Bryce David from the University of North Carolina. David wrote, "Every quantum transition taking place in every star of every galaxy, in every remote corner of the universe, splits our local world on Earth into myriad copies of itself." It was too much for Wheeler. He refused to support the multi-world interpretation, to which he was inclined initially, and already in the 1970s he spoke. In the end, I had to reluctantly withdraw support for this hypothesis. Because, I'm afraid, it carries too much metaphysical load. Ironically, it was at this moment that the idea was experiencing a revival and development in the field of cosmology and quantum computing. The power of this interpretation began to be recognized even by those who were not ready to fully support it. John Bell noted that people, of course, multiply with the worlds, and the inhabitants of a particular branch of it should feel only what is happening in this branch, and reluctantly admitted that there might be something in this idea. The multi-world interpretation seems to me an extravagant and, first of all, an extravagantly vague hypothesis. I'm almost ready to dismiss it as ridiculous. And yet, perhaps she has something to say in connection with the Einstein-Podolsky-Rosen paradox. And, it seems to me, it would be worthwhile to formulate some strict version of it and see if this is really the case. In addition, the existence of probable worlds would perhaps allow us to feel more comfortable about the existence of our own world, which in some respects seems very unlikely. A strict version of the multi-world interpretation appeared thanks to David Deutsch from Oxford. In fact, she laid a solid foundation for Schrödinger's version, although the daughter did not know about it, formulating her interpretation. In the 1970s, my daughter worked with DeWitt, and in 1977, at the organized last conference, I met with Everett. This was the only time Everett presented his ideas in front of a large audience. Convinced that multi-world interpretation is the right way to understand the quantum world, Deutsch became a pioneer in the field of quantum computing. Not because he was interested in computers, but because he believed that the creation of a quantum computer would prove the reality of a multi-world interpretation. And here we come back to the variant of the thought experiment with Schrödinger's cat. According to Everett, there is only one code until the infernal machine is triggered, and after that the entire universe splits in two. Similarly, as David pointed out, an arbitrary electron in a distant galaxy, faced with a choice of two or more quantum trajectories, causes the splitting of the entire universe, including you and me. The Deutsch-Schrödinger variant assumes an infinite variety of universes corresponding to all possible solutions of the quantum wave function, the so-called multiverse. So, in the experiment with the cat, there are many identical universes in which identical experimenters build identical infernal machines. These universes remain identical exactly until the moment when the machine works. After that, in some universes, the cat dies, in some it continues to live, and also happens in subsequent stories. Under no circumstances can parallel worlds communicate with each other. Or can they? Deutsch argues that when two or more previously identical universes under the influence of quantum processes are forced, as in the experiment with two holes, to become different, interference occurs between them for a while. With the development of universes it is suppressed. It is this interaction that causes the observed experimental results. Deutsch's dream is to see a working quantum computer that will track some quantum phenomenon involving interference occurring inside his brain. Deutsch claims that an intelligent quantum computer will be able to remember the experience of temporary existence in parallel realities. Of course, this project is still very far from being implemented, but Deutsch also has a much simpler proof of the existence of the multiverse. The qualitative difference of a quantum computer is that the keys inside it are in a superposition of states. A traditional computer consists of a set of keys of electrical circuit components that are either on or off, which corresponds to the digits 1 and 0. This allows calculations to be performed by manipulating strings of numbers in binary code. Each key is called a bit. And the more bits we have at our disposal, the more powerful the computer is. 8 bits make up a byte, and today computer memory is measured in billions of bytes. Gigabytes. Strictly speaking, since we work in binary code, a gigabyte equals 2 to the 30th power of bytes, but this is usually ignored. But in a quantum computer, each key is an object that can be in a superposition of states. As a rule, it is an atom, but in principle it can be considered that it is an electron whose spin can be positive or negative. The difference is that in a superposition, an electron has both positive and negative spin. Represents both 0 and 1. Each key here is called a qubit. Due to this quantum property, each qubit is equivalent to 2 bits. At first glance, it is not particularly impressive, but in fact it is significant. So, if you have 3 qubits, you can organize them in 7 ways. 000001001001110 1011011111. The superposition includes all these options. Thus, 3 qubits, equivalent not to 6 bits, 2 multiplied by 3, but in 8, 2 to the third power. The equivalent number of bits is always 2 to the power of the number of qubits. Only 10 qubits would be equivalent to 2 to the 10th power of bits, that is, strictly speaking, 1024, but usually this number is called a kilobit. Such geometric progressions grow very quickly and go to infinity. A computer with only 300 dead would be equivalent to a traditional computer with more bits than the number of atoms in the observable universe. But how would such a computer be able to perform calculations? This question has become very urgent, since the first simple quantum computers, including several qubits, have already been built and demonstrated to work in accordance with expectations. Are they actually more powerful than traditional computers with the same number of bits? Deutsch's answer is that calculations are carried out simultaneously on identical computers in each of the parallel universes corresponding to our superpositions. For a 3-bit computer, this means 8 superpositions of computer scientists working on the same task using identical computers to get an answer. It is not surprising that they should cooperate in this way, since all experimenters are identical and have identical reasons to engage in the same task. It's not too hard to imagine. But if we build a 300-qubit machine, and this will certainly happen someday, then if Deutsch is right, we will get a collaboration between a huge number of universes, exceeding the number of atoms in our visible universe. The question arises, is the metaphysical load not too great or too great? Everyone chooses the answer himself, but if you think it's too much, then you'll have to explain in some other way why quantum computers work. Most quantum computer specialists prefer not to think about these issues. But there is a group of scientists who are used to thinking about even more than 6 impossible things every day before breakfast. And this group is cosmologists. Some of them have adopted the multidimensional interpretation as the best way to explain the very existence of the universe. The starting point for them is the fact noted by Schrödinger that there is nothing in the equations that would indicate the collapse of the wave function. At the same time, they mean one single wave function, the one that describes the whole world as a superposition of states, the multiverse, which is a superposition of universes. The first version of Everett's dissertation, subsequently revised and shortened on Wheeler's advice, is called the theory of the universal wave function. By universal in this case, the author meant literally universal. Universe, entity. He wrote, since universal justice is asserted, the description of the state function, it is possible to consider the state functions themselves as fundamental objects and even consider the state function of the entire universe. In this sense, this theory can be called the theory of the universal wave function, since it is assumed that all physics stems from this one function. Here, with our current goal in mind, the state function is just another name for the wave function. All physics means everything, including us observers in physical jargon. Cosmologists rejoice in this theory not because they were also included in the wave function, but because such an idea of a single, non-collapsing wave function is the only way to describe the entire universe in quantum mechanical language, without losing compatibility with general relativity. In a brief version of his dissertation published in 1957, Everett came to the conclusion that his formulation of quantum mechanics could therefore prove to be a fruitful basis for the quantization of general relativity. Although his dream has not yet come true, it inspired cosmologists to work actively in the mid-1980s. But still, this theory drags a lot of weight behind it. The universal wave function describes the position of each particle in the universe at a particular moment in time. But it also describes all possible positions of these particles at this moment. And all possible positions of each particle at any other time, although the number of possible options is limited by the quantum discreteness of space and time. Out of this unimaginable multitude of possible universes, many variants will turn out to be those where the existence of stable stars and planets, as well as people who would live on these planets, is impossible. But at least some universes will be more or less similar to ours, as it is often depicted in science fiction and in fiction in general. Deutsch pointed out that according to the multi-world interpretation, any world described in any literary work actually exists somewhere in the multiverse, provided that it obeys the laws of physics. Somewhere there must be, for example, the world of Wuthering Heights, but not the world of Harry Potter, and that's not all. A single wave function describes all possible universes at all possible points in time. But it does not say anything about the transition from one state to another. Time does not flow. Strictly speaking, one of the Everett parameters, called the state vector, includes a description of the world in which we exist and all the records of the history of this world, from our memories to fossils and light reaching us from distant galaxies. There must also be another universe, exactly the same as ours, but shifted in time, say, by 1 second, or an hour, or a year. But there is no indication that any universe is moving from one moment of time to another. In the second universe, described by the universal wave function, there must also exist me, who has all the memories that I have at the first moment of time, plus memories corresponding to the next second, or hour, or year, or any other interval. However, it is impossible to say that all these variants of me are the same person. Different temporal states can be ordered by the events they describe, thus determining the difference between the past and the future. But the universe does not change from one state to another. All states simply exist. Time, as we used to perceive it, in Everett's multi-world interpretation, does not flow. However, as far as I understand, it's time for us to change something. It's time to look for a different kind of consolation. And this time we will look for it in decoherence. In order for decoherence to occur, it is necessary that something be coherent first. Physicists clearly know what they mean by coherence. And proponents of interpretation with decoherence argue that it is coherence that makes the quantum world behave the way it does. As usual, the experiment with two holes will help us shed light on what is happening. Light or any other waves that diverge in different directions from the two holes initially come from the same source and are therefore synchronous with each other. The holes simply direct these coherent waves along different trajectories, and the difference in the length of these trajectories affects how the two sets of waves interact with each other. Here they converge in one phase, there they converge in different phases. The crests and troughs of the waves are always arranged regularly, according to clear rules, and this allows the waves to interact with each other so that the result is an equally regular pattern of light and shadow. If the waves are not coherent, for example, the light from two torches illuminating the wall is not coherent, then there is no interference pattern. Actually, there is interference between them, but everything is so mixed up that there is no regular pattern. According to the decoherence interpretation, quantization disappears precisely when everything is mixed up. But the light from two torches has never been coherent. He was not coherent. There is another useful analogy. The so-called Mexican wave, which can sometimes be seen at stadiums. If every spectator on the podium raises and lowers his hands randomly whenever he wants, you will see only a chaos of waving hands. But if each person raises and lowers his hands at the right moment, following his neighbors, then a wave sweeps through the stands of the stadium. This wave is coherent. Arbitrary hand waving is not coherent. So the term decoherence, strictly speaking, is not very appropriate in a quantum context. Perhaps it would be more reasonable to call this model an incoherent interpretation of quantum mechanics, but then its supporters might think that this name gives the listener a false impression of their favorite idea. If the fans of this idea are right, the boundary between quantum and the ordinary world is determined by coherence, not size. Bohr and his colleagues were very vague about this, and there are reasons for that. They could reasonably argue that an object as large and complex as a cat is too large to be in a quantum superposition, while individual atoms can be in it. But if we start coming up with our own versions of a thought experiment with a cat in a box, then where will we need to draw the line? Is the flea big enough to know for sure whether it is alive, dead, or in a superposition state? And the microbe? No one knew that. One person accepted the challenge and decided to find the answer to this question. Anthony Leggett, who worked at the University of Sussex in the late 1960s and 1970s, firmly decided to develop experiments that would allow us to check whether the rules of quantum mechanics are still applicable to the description of the behavior of so-called macroscopic objects. Big enough to be picked up in your hand. Or even more. This led Leggett to create superconducting quantum interference devices. With the squid device. A typical such device was about the size of an engagement ring. It was really possible to take it, I kept it, but since the device had to be cooled to ultra-low temperatures to work, it was impossible to hold it in the working state in your hand. The electric current in a superconductor, once started, flows forever. The behavior of such a current flowing through the squid ring can be monitored. It can be corrected with the help of electric and magnetic fields. Experiments have shown that an electron wave running around the ring behaves like a single quantum object, which is about 100 million times larger than an atom. And probably bigger than bacteria or even fleas. Thus, Leggett reached the first goal, but did not stop there. Perhaps you think that such a wave can run along the ring in one direction or the other, but not in both directions at the same time. You're wrong. Experiments conducted at the beginning of the 21st century demonstrated effects indicating wave motion in both directions simultaneously. Not two waves moving in opposite directions, but the same wave going both ways at the same time. Superpositions. So the quantum nature of an object determines not its size, but the fact of the coherence of the waves. Since then, work in this direction has progressed significantly, which brought Leggett a Nobel Prize and a knighthood. The SCUT device is becoming larger and finds practical application in medicine as sensitive detectors of magnetic fields generated by the human body, as well as potential components of quantum computers. For us, it is important to note that while the waves are coherent, they behave like macroscopic examples of well-defined quantum states. But when the temperature rises and the waves decoherate, they cease to demonstrate quantization. In Bohr's language, we can say that decoherence, apparently, causes the collapse of the wave function. Therefore, some physicists believe that the decoherence interpretation is the same Copenhagen interpretation, but under a different name. However, the key role of superposition and entanglement in the strict formulation of interpretation with decoherence is overlooked. Superposition and entanglement, two sides of the same coin. When two particles interact, they become entangled. And from that moment on, everything that happens to one of them affects the other. In essence, they become a single object. Similarly, a wave running along the squid ring simultaneously in both directions can be considered two waves in a superposition entangled with each other. The result of this is a single quantum object, a wave traveling along the ring not in one direction, but in two at once. It is not surprising that interpretation with decoherence appeared only in the 1980s simultaneously with experiments that established that entanglement is the correct description of the way our world functions. What actually happens when a pure quantum object interacts with the outside world and decoheres? It becomes not less, but more confusing. Imagine a single particle in a pure quantum state. Should it scatter on another particle, or at least interact with a photon of light, how does it become entangled? If either of the two entangled objects interacts with the third, all three become entangled, and their quantum states end up in superposition. Entanglement spreads, as they say, faster than a forest fire. In practice, there is simply no such thing as a pure quantum system separated from the outside world. Except in very special circumstances, such as experiments with squids. And there are intricate systems of both. A superposition of everything that has ever interacted with the original particle, and everything that it has ever interacted with, as well as everything that it has ever interacted with or contacted. Decoherence actually means linking everything in the world, in the universe, into a single quantum system. We no longer observe the quantum state of a once isolated particle, because it has mixed with everything else. Because of the resulting incoherence, it is extremely difficult to understand the fundamental quantization of everything except the simplest systems. Mathematicians will tell you that in principle this is possible, since the equations describing the quantum world are reversible in time. But don't hold your breath waiting for someone to try to do it. As noted by Philip Bohl, decoherence very quickly leads to an incoherent state equivalent to a superposition of such a number of quantum states that exceeds the number of elementary particles in the observable universe. Bohl asked whether it is possible to declare a problem strictly unsolvable just because there is not enough information in the universe to solve it. Bohl also gave some estimates of the time required for the system to decoherence. Decoherence is faster for large objects, because there are more pieces in them that can interact with other objects and with each other. For dust particles floating in the air and bombarded by surrounding molecules, decoherence takes less time than it takes for a photon moving at the speed of light to travel a distance equivalent to the diameter of a proton. Even in interstellar space, a speck of dust floating freely and interacting only with photons of relic radiation decoherates in about a second. For all practical purposes, decoherence is instantaneous and inevitable. This also applies to Schrödinger's famous cat. To be both dead and alive at the same time, this cat must be prepared in some almost incredible coherent state of pure quantum. It's one thing to prepare a squid in a pure quantum state and quite another to do it with a cat. And if you succeed, then the quantum cat decoherates either into a dead or a living cat faster than a speck of dust floating in the air decoherates. This also invalidates one of the philosophical objections to the Copenhagen interpretation. Taken literally, the Copenhagen interpretation asserts that nothing is unreal unless it is observed or measured. Let's say the code in the box can exist in a superposition of states. But then, opponents of this idea ask, does the moon exist when no one is looking at it, or is it in a superposition of all possible quantum states all the time? Did it exist in this sense before the emergence of life on Earth? There were no satisfactory answers to these questions. Interpretation with decoherence gives them. Photons of relic radiation, not to mention sunlight, are quite enough to cause decoherence and make the moon real. However, this is not the end of the story. There were people who, instead of using the idea of decoherence only in the here and now situation, so that it does not mean here and now in a confusing universe, decided to apply this way of thinking to the whole story. Or to all the stories of the universe. As a result, what was previously an independent interpretation of the interpretation of non-contradictory stories has become an interpretation of incoherent stories. But I will start from the point where it is not about inconsistency. It is based on the idea that we know about the quantum world, or the world in general, only what we can see and measure. Before conducting an experiment or measurement, we can only calculate the probability of its various outcomes. But it is worth taking a measurement, and we get a certain result, in a sense, selected from a variety of possible options. The argumentation of the approach associated with non-contradictory stories is that whatever the result of the measurement, that is, whatever happens in the world, all this must be consistent with the past, with history. When we look at the interference pattern obtained in the experiment with two holes, all we can say for sure is that the pattern on the screen is consistent with the fact that the waves passed through the hole and interfered with each other. When light knocks electrons off the metal surface, we can only say that this is consistent with the fact that light came in the form of photons. The cosmological consequences of all this were widely discussed in the scientific community. In particular, Stephen Hawking and his colleagues participated in the discussion. Hawking described the traditional approach to understanding the universe in quantum terms as bottom-up analysis. You start by trying to guess what the universe might have looked like at the very beginning, being a superposition of wave functions, and then you try to figure out how it moved into the state in which we see it today. Hawking himself preferred an alternative top-down approach, in which you start with the current state of the universe and step by step, coordinated, move along the path it has traveled into the past, trying to determine which wave functions contributed to its emergence. The problem is that there may be, and usually there is, more than one unique path that can lead to the observed result. There are more than one non-contradictory stories. There is no single unique history of the universe that could be reconstructed in this way. If in the electronic version of the experiment with two holes, some electron reaches a certain point on the screen, there is no way to determine exactly which hole it went through. Both possible stories are quite consistent with what we are observing. And the world as a whole is much more complicated than the two-hole experiment and opens up a much wider selection of non-contradictory stories. I will come back to this, but first we will answer the question. And where does the wildness appear in this plot? If each dimension, each quantum interaction chooses one of a number of possible histories, then one can imagine restoring the trajectory back in time to the Big Bang itself. And maybe even further, but I won't go that far. Moreover, decoherence, and this is exactly it, will select non-contradictory versions of the story. In the beginning, everything is possible, but as soon as the first quantum interactions occur, some possibilities are eliminated, and the diversity of different universes decreases. That is, the diversity of non-contradictory past universes decreases. This continues up to the present time, choosing the history of our universe, but this is fundamentally not only ours from among the possible worlds. The approach associated with incoherent stories does not choose a unique universe. No. We return again to the variation on the theme of many worlds, but we come to it in a different way. The possibility of using decoherence to transform the idea of many worlds into the idea of many stories seemed tempting to some physicists, since it allowed them to get rid of excess baggage in the form of parallel equally real worlds, and replace them with different stories that existed only in the form of ghostly states among probabilities. But in the mid-1990s, it became obvious that things were not so simple. At one conference, Lee Smolin from the Canadian Institute of Theoretical Physics Perimeter heard a speech by Faye Docker on the topic of these possibilities. He had an idea, which he later described in the book 3 Roads of Quantum Gravity. Although the classical world we are observing, in which particles have certain coordinates, is perhaps one of the non-contradictory worlds, and described by some theoretical solution, the results of Docker and Adrian Kent show that there must also be an infinite number of other worlds. Moreover, there were an infinite number of non-contradictory worlds that were classic up to this point, but in 5 minutes they will be completely different from our world. Even more worryingly, there were worlds that were classical now, but were an arbitrary mixture of superpositions of classical worlds at any point in the past. If the interpretation of non-contradictory stories is correct, we have no right to conclude from the existence of fossils that dinosaurs roamed our planet 100 million years ago. All stories are equally real, and what we perceive as the only true story of our world depends on the questions we ask. Just like in the experiment with electrons, if we look for waves, we will find waves. And if we look for particles, we will find particles. If we look for evidence of the existence of dinosaurs in the past, we find a story that is consistent with the existence of dinosaurs in the past. This doesn't necessarily mean that there were actually dinosaurs in the past. This only means that the current state of the world does not contradict the possibility of the existence of dinosaurs in the past. As Smolin said about this, it turned out to be a theory in which we can formulate answers, but not questions. Not that it suits both ours and yours, but depending on your preferences, you can see in the interpretation with decoherence a variant of either the Copenhagen or the multi-world interpretation. Don't worry if you don't like any of them. Perhaps you can find solace in the ensemble interpretation. The ensemble interpretation was the first and simplest alternative to the Copenhagen interpretation. It was her, by the way, that Albert Einstein preferred. Trying to consider the quantum theoretical description as a complete description of individual systems, we come to an unnatural interpretation of the theory. If we take the point of view that such a description refers to an ensemble of systems, and not to individual systems, then there is no need for such unnatural interpretations. Leslie Ballantine of Simon Fraser University in Canada, the main modern proponent of this idea, explains that Einstein's criticism of the interpretation, which many physicists accept by default, was due to the fact that the quantum state function, the wave function, does not describe a separate system, but rather an ensemble of similar systems. But this interpretation doesn't really interpret anything. She simply claims that everything that seems strange in the quantum world can be explained from the standpoint of statistics. This is sometimes called statistical interpretation. Rather, it resembles a policeman at a crime scene, persuading crowded onlookers there is nothing to see here, please come in. This refers to statistics related to specific ensembles. But the ensembles themselves are not at all what most people come to mind at the mention of this term. In everyday language, an ensemble is a group of objects that have a common property or work together, for example, a musical string ensemble. For a statistician, an ensemble can be, for example, a set of 600 identical dice. If you throw them all at the same time, then according to the laws of probability we can expect that about 100 sixes, about 100 fives, about the same number of 4s, 3s, 2s and 1s will fall out. But you can get the same statistical result in a different way. Take one perfect dice and roll it 600 times. Then you can expect that the 6 will fall out about 100 times, the 5 also about 100 times, and so on. It is this kind of ensembles that quantum physicists have in mind. A container filled with gas molecules cannot be called an ensemble. But a lot of identical containers with gas, over which the same experiment is carried out, is possible. Ideally, you should conduct exactly the same experiment on the same particle many times, tracking the result of each of these attempts. This is the ensemble. The results will follow a probability distribution according to the rules that Max Born developed. It would be very difficult to carry out such an experiment in practice, but that's not the point. Imagine not a million electrons simultaneously passing through the installation of a double-slit experiment and being registered on the other side, but the same electron passing through the installation a million times. At the same time, the position of the point through which the electron passes on the other side is marked each time. The fundamental point that supporters of this interpretation are very fond of is that particles in this case are always real particles in the everyday sense of the word. The wave function here is not applicable to individual particles, so each individual electron, for example, has either positive or negative spin. But when you have a lot of particles, the probability of detecting each option when checking an individual electron is, all other things being equal, 50-50. There is no wave-particle dualism, there is no superposition, and there are no dead and living cats. Of course, it would be difficult to conduct an experiment using the same cat 100 or more times. But if you do this with 100 cats in turn, then, according to the ensemble interpretation, half of them will survive, and half will die, but not a single cat will be in a superposition. Sounds tempting. Here it is, common sense. But, as Ewan Squires pointed out, we cannot claim to have solved the interpretation problems. We just ignored them. Separate systems exist. But how should this work in practice? As often happens in quantum theory, the waters become noticeably turbid when trying to understand what happens when a system, in this case an ensemble, is being investigated, or when it interacts with the outside world in some other way. The preparation of the system involves some participation of randomness, and observing it adds another layer of randomness. We are once again faced with the problem of determining where the system ends and the outside world begins. As in the case of entanglement, which extends to the entire universe in interpretation with decoherence. An example of such interaction with the outside world, which sometimes leads to the support of an ensemble interpretation, can be the so-called experiment with a kettle under observation. The key to this idea is that although the equations of quantum physics describe the probability of detecting a system in one state or another, they do not say anything about how systems make the transition from one state to another. There is nothing in the equations that describes the collapse of the wave function. And no experiment has ever recorded a single wave function in the process of collapse. Back in 1954, Alan Turing pointed out that the quantum system, which is constantly monitored, will never change. He wrote, "It is not difficult to show with the help of standard theory that if a certain system begins to be observed in its own state, the agent state of some observable measurement of this observable is carried out n times per second, then even if the state of the system is not stationary, the probability that it, say, in 1 second will be in the same state, strive for unity as n strives for infinity." That is, continuous observations will hinder any movement. Physicists try to explain this in different ways. Here is one of the versions. Imagine a system in a well-defined state with a probability wave propagating outward and gradually increasing the probability of detecting this system in some other state. If you wait a little longer, then take a look. You will probably be able to see her in a different state. But if you look at it very quickly, then the probability simply will not have time to change and the system will remain in the same state. It cannot be in an intermediate state, because there are no intermediate states. This means that the wave will have to start spreading again, from the same position. Look at the system often enough, and it will never change. A quantum teapot will never boil if you look at it all the time. This is what Turing predicted, and his prediction has already been tested experimentally. All such experiments contain variations of the same theme. As a rule, a teapot consists of several thousand ions of some element, for example, beryllium, captured by electric and magnetic fields. An ion is an atom devoid of one or more electrons and resulting in a positive charge, making it easy to manipulate with the help of such fields. The ions are prepared in advance in such an energetic state from which they want to leave, having dropped to a lower energy level. The state of the system can be monitored using an ingenious technique using lasers, which allows you to determine how many ions have passed into the ground state over a certain period of time. In one typical experiment, after 128 milliseconds, it turned out that half of the ions had passed into the ground state. If the laser looked at the system 64 milliseconds after the start, then only a quarter of the ions turned out to have passed into the ground state. If the laser flashed every 4 milliseconds and checked the system 64 times in 256 milliseconds, then after this period of time it turned out that almost all the ions were in their original state. In the probability categories corresponding to our wave function, this refusal to boil is explained by the fact that after 4 milliseconds, the probability that a certain ion has already passed into the ground state is only 0.001% So 99.99% of the ions should still remain at level 1. And this is true for every interval of 4 milliseconds. The shorter the interval between observations, the stronger the described effect. Wave functions never collapse if they are observed. Then why should we assume that they collapse at all? Bellin 10 argues that they do not, and that the phenomenon described earlier is experimental evidence in favor of an ensemble interpretation. However, the ensemble interpretation has one serious problem. It explicitly states that the wave function is inapplicable to individual quantum objects and that there is no superposition of states. But experimenters today calmly, in a working manner, manipulate individual quantum objects, for example, electrons, in situations such as quantum computing, where they seem to follow the description of the wave function. And the squat ring seems to be able to demonstrate a single macroscopic quantum object. The electron wave runs along it simultaneously in both directions, being in superposition. I used to think that this was a fatal blow to the idea of an ensemble interpretation, but Lee Smolin revived it in a new incarnation. The new version of the ensemble interpretation includes the concept of non-locality, which, as already experimentally shown, is a key property of the universe. The Einsteins probably would not have been happy with such metamorphoses of the interpretation he supported. But Smolin likes them so much that he, not at all embarrassed, calls his version a real ensemble interpretation. The key difference is that if in the traditional ensemble interpretation the members of the ensemble cannot all exist at the same time, then in Smolina's version they are simultaneously real. To make this shorter and to the point, we should add one slang word that physicists use. Possible quantum components of the ensemble, say, hydrogen atoms, they call biable from biable to be able. Because these are objects that could in principle exist. But, as in the case of throwing one dice 600 times instead of throwing 600 dice at once, all of them do not have to exist at the same time. The concept, which, out of respect for Smolin, I will call a real ensemble interpretation, says, all the biable that make up the ensemble actually exists in nature at the same time, like 600 dice that are thrown together, and not like one dice that is thrown 600 times in a row. Any quantum system at any given time is characterized by a very specific state of affairs, determined by the values of biable. Smolin begins with a reasonable principle, according to which everything that is supposed to affect the behavior of a real system in the universe itself must also be a real system in the universe. It is unacceptable, he says, to imagine that there is some creepy way in which potentials affect realities. In the interpretation with the pilot wave, for example, the wave represents a real property of the universe, a kind of beable, and not some kind of creepy probability wave. But this interpretation conflicts with another postulate that Smolin put forward. There should be no unrequited action anywhere in nature. In fact, this is an extension of Newton's third law, according to which in classical systems actions and counteractions are equal in magnitude and opposite in direction. But in the interpretation with the pilot wave, the wave affects the particle, but the particle does not affect the wave, does not counteract. At the same time, in the ensemble as Smolin draws it, the beables that make up the ensemble mutually influence each other, generating the behavior that we see in such experiments as the experiment with two holes. And if all the components of the ensemble are real, then there is no reason why there cannot be new interactions between them, in the sense that they have not been discovered before. Smolin gives an example of hydrogen atoms in their minimum energy state, which is called the ground state. There is an ensemble of all such hydrogen atoms in the universe, a real ensemble of real labels. Its components interact with each other in a non-local way, through which biable copy each other's state in accordance with the probability rules associated with these quantum states. The copy probabilities do not depend on exactly where the components are located in space, but depend on the way in which the biable are distributed in the ensemble. Quantum statistics allows you to make a list of positions in which hydrogen atoms will be detected in the ground state, but does not allow you to say which hydrogen atom is in which location. Smolin was able to show mathematically that based on a few simple rules about how pairs of biable affect each other, this process allows us to obtain all the observed behavior of quantum systems. And also explain why objects such as cats and humans cannot be in superposition. Quantum mechanics, Smolin says, is applicable to small subsystems of the universe that exist in many instances, like hydrogen atoms in the ground state. But macroscopic systems, such as cats and humans, have no copies anywhere in the universe, and they are not affected by the copying process that takes place with the participation of interacting quantum beables. In this sense, they simply have nothing to interact with. Several interesting conclusions follow from this. First, the universe must be finite. There would be countless copies of you in an infinite universe. So the interactions described by Smolin's equations would affect you, and you would behave like quantum particles. Secondly, Smolin deduces from simple mathematical rules not only the Schrödinger wave equation, but also the laws of classical mechanics, Newton's laws and the like, as an approximate version of quantum mechanics. However, Smolin suspects that quantum mechanics itself is an approximate version of some deeper description of the universe. This prompted him to dive deep into these murky waters, and he goes so far as to claim that if this is the case, then the exchange of signals at superluminal speed may well be possible. The fact that we have not yet come to a final version of the theory is evidenced by one moment. You may have already noticed that the interaction of biable implies the existence of a unique cosmic time so that these interactions can occur simultaneously. And this requires an extension of the theory of relativity. Quantum physics, Smolin says, should be an approximate version of some cosmological theory that is formulated in a different language. Perhaps we should look for these fundamental laws in experiments involving systems that exist in the universe in a small number of copies, that is, on the border between the microscopic and macroscopic worlds. It is possible that experiments with quantum computers would allow us to understand whether there are copies of them somewhere in the universe. There may be real observable effects generated by corrections of quantum physics, which depend on the size of the ensemble. All this sounds wild, but Smolin can remind us of something. There were times when it was difficult for people to believe that the sun affects the dynamic behavior of planets, because it implies incomprehensible actions at a distance. As I have already mentioned, even Newton did not try to explain how it all works, limiting himself to the famous answer of the non-thing hypothesis. I don't invent hypotheses. The present ensemble interpretation provides for a new type of non-local interaction between biables, but this should not bother us more than the fact that just a little over 100 years ago the interaction between the Sun and the Earth was described by some new type of interaction, and now it is described by the general theory of relativity. Not physics, not locality seems creepy because of its strangeness. But for a growing number of physicists, it has become as accepted a fact as gravity. After all, it's not that hard to digest before breakfast. Interaction that does not care about space is an established property of the surrounding world. And what can we say about interactions that don't care about time? Can we find solace here? The roots of the transactional interpretation of quantum mechanics lie in the mystery of the nature of light, which interested Albert Einstein. It was thinking about the nature of light that led Einstein to create a special theory of relativity, and this alone is enough to take the question seriously. The realization led to the special theory of the great physicist that from the equations describing the behavior of light and all other electromagnetic radiation, it follows, the speed of light is the same for everyone and is constant. Now this constant is written as c. If you point a flashlight beam at me, and I just stand next to you, then when measuring the speed of light from the flashlight, I will get c. But even if I rush to you or from you at high speed, I will still get the value when measuring the speed of light of the flashlight c. From this simple fact, Einstein revealed the theory of relativity. The equations, which among other things state that the speed of light is the same for any observer, are known as Maxwell's equations and are named after the 19th-century physicist who discovered them. But James Clerk Maxwell's equations have another curious property. They are symmetrical in time. In any problem involving electromagnetic radiation, for example, radiation associated with a moving electron, these equations always have two solutions. One describes a so-called lagging wave that emanates from a source and moves forward in time to be absorbed somewhere far away in the outside world. Another describes a leading wave that comes from absorbers somewhere out there in the outside world and converges from the future to what we perceive as a source of radiation. In this case, a moving electron. Most physicists simply do not pay attention to this advanced solution. But in 1909, Einstein said, in the first case, the electric field is calculated from the totality of the emission processes. In the second, according to the totality of absorption processes. You can always use either of the two equalities, just as you can mentally remove the absorbing body. Hence, it cannot be concluded that the lagging solution is more special than the solution, which is a linear combination of lagging and advancing waves. You can mentally remove a body that absorbs radiation, and at any distance. This applies not only to electronic devices interacting with their neighbors, but also, for example, to television signals propagating from the Earth through the universe. The equations describing this process always include solutions describing the leading waves converging from the depths of the universe of the contours from which these signals were transmitted. Here there is a hint of a type of non-locality that differs from what we have seen before. Or the same one. But, of course, Einstein in 1909 did not think about it. One of the very few people who took this idea seriously was Richard Feynman, who was a graduate student at Princeton in the 1940s. On the advice of his supervisor John Wheeler, he developed the idea that, interacting with another charged particle, an electron, as it were, descends into the future and into the past along half a wave. Where this wave meets another charged particle, the latter emits back and forth in time its own halves of the wave. According to the Feynman version, two half-waves, interfering, compensate for each other everywhere, except in the space between these two particles, where they amplify and form a full wave. When Feynman gave a talk on this topic at Princeton, Einstein and Wolfgang Pauli were among the listeners. Pauli said he didn't think the idea would work and asked Einstein if he agreed with that. No, Einstein said, it just seems to me that it would be very difficult to create an appropriate theory for the gravitational interaction. Despite such support, the idea remained unclaimed for a long time. Because no one simply believed in the waves coming from the future. But in the late 1970s, John Kramer, a lecturer at the University of Washington in Seattle, who was captured by Feynman's idea while still in graduate school, suddenly realized how it could be incorporated into quantum mechanics. As it often happens, Kramer's thought seems obvious, but only from the moment someone expresses it. Kramer was prompted by the idea of what happens to a probability wave in a quantum system when the particle with which it is associated is registered in a certain location, from where the wave in all other places learns that at this moment it is necessary to disappear. Kramer drew an analogy with a bottle that is thrown from a Florida beach into the Atlantic Ocean. Imagine that this quantum bottle, and that it disappears in a wave that spreads over the entire ocean and reaches Europe. The bottle ends up somewhere on a beach in England, and at that very moment the waves that have spread all over the ocean disappear. Kramer realized that there must be advancing and lagging waves, and that these waves produce quantum handshakes everywhere. He realized that only those lagging waves that produce an echo in the form of advancing waves can affect the position of particles. Their mysterious quantum mechanical transfer from point A to point B, or the transition from one energy level to another without moving through the space separating them. The waves from the bottle in England traveled back in time to Florida across the ocean to establish a unique connection and extinguish all other waves. Kramer saw here a similarity to the pilot wave model, in which waves show particles where to move, but in which, crucially, there is no backward in time handshake confirmation. This also explains the mystery of the EPR. Two particles that once interacted with each other, subsequently remain connected by a handshake, that is, confirmed contact between them and the place of their interaction. All this is linked to the correct, in Kramer's opinion, description of the famous Schrödinger equation. To apply the theory of the absorber to quantum mechanics, we need some kind of quantum equation, which, like Maxwell's equations, has two solutions. One of them corresponds to a wave of positive energy flowing into the future. The second describes a wave of negative energy flowing into the past. At first glance, the Schrödinger equation does not correspond to this description, since it describes the flow in only one direction, which we interpret as the direction from the past to the future. However, any physicist at the university is told that the widely used version of the equation is not complete. The majority quickly forgets this. Even the quantum pioneers of quantum science realize that the Schrödinger equation does not take into account the requirements of relativity theory. In most cases, it doesn't matter. That's why physics students and even most quantum mechanics specialists use a simple version of the equation and don't worry about anything. However, the full version of the wave equation, which properly takes into account relativistic effects, is much more like Maxwell's equation. In particular, it has two sets of solutions. One of them corresponds to the well-known simple Schrödinger equation, the second is a kind of mirror image of the Schrödinger equation describing the flow of negative energy into the past. This duality is clearly manifested in the calculation of probabilities in the field of quantum mechanics. The properties of a quantum system are described by a mathematical expression called a state vector, and, in turn, is described by the Schrödinger wave equation. In general, it is a complex number, that is, a number that includes the square root of -1 and. If a and b are ordinary numbers, then a plus and multiplied by b, as well as a minus and multiplied by b, will be a complex number. The probability calculation necessary to determine the chance of detecting, for example, an electron in a certain place at a certain time, is reduced to calculating the square of the state vector corresponding to this particular state of the electron. But calculating the square of a complex variable does not mean simply multiplying it by itself. Instead, you should create another variable, a mirror image of the first one, called a complex conjugate quantity, by changing the sign in front of the imaginary part. A plus will become a minus and vice versa. Thus, a minus and multiplied by b and a plus and multiplied by b are complex conjugate quantities. To calculate the probability, these two complex numbers are multiplied together. But for equations that describe a change in the system over time, the act of changing the sign of the imaginary part and finding a complex conjugate number is equivalent to changing the direction of the flow of time to the opposite. The basic probability equation proposed by Max Born back in 1926 contains an explicit reference to the nature of time and to the possibility of the existence of two types of Schrödinger equations, one of which describes advancing waves, and the other, lagging. From this follows the remarkable fact that starting as early as 1926, whenever a physicist takes a complex conjugate to a simple Schrödinger equation and uses it to calculate quantum probability, he, without realizing it, takes into account the solution of these equations with a leading wave and the influence of waves moving backwards in time. From the point of view of mathematics, Kramer's interpretation of quantum mechanics does not have any problems. Because all the mathematics, up to the Schrödinger equation, is exactly the same there as in the Copenhagen interpretation. The difference here is literally only in interpretation. Kramer describes a typical quantum transaction as a handshake of a particle with another particle located at another point in space and time. He starts with the idea of an electron emitting electromagnetic radiation that is absorbed by another electron. But this description works just as well for the state vector of a quantum object, which starts in one state and ends in another, as a result of some kind of interaction. For example, for a vector, the state of a particle and deflated by a source on one side of an experiment setup with two holes and absorbed by a detector on the other side of it. One of the difficulties of such a description in ordinary language is how we should interpret interactions going simultaneously in both directions in time. And therefore, what happens is instantaneous from the point of view of an ordinary clock in the everyday world. Kramer does this by remaining essentially timeless and using a semantic means, a description in terms of a kind of pseudo-time. This is nothing more than a semantic tool, but it certainly helps most people to build a coherent picture in their minds. It works like this. When a quantum emitter object interacts with the surrounding world, it tries to do so by generating a field that is a time-symmetric mixture of a lagging wave going into the future and a leading wave going into the past. For the sake of getting a clear picture, we ignore the advancing wave and follow only the lagging wave. It moves into the future until it meets another object, an absorber with which it can interact. During the interaction, the second object generates a new lagging field, which exactly compensates for the first lagging field. As a result, there is no lagging field in the future of the absorber. But the absorber also generates a negative leading wave going back in time to the emitter along the trajectory of the initial lagging wave. At the emitter, this leading wave is absorbed, causing the first object to respond, in which it emits a second leading wave back into the past. This new leading wave completely compensates for the original leading wave. So before the start of this whole process, there is also no effective radiation going back to the past. There remains only a double wave connecting the emitter and the absorber, and half consisting of a lagging wave carrying positive energy into the future, and the other half, of a leading wave carrying negative energy into the past, in the course of negative time. Since minus by minus gives a plus, this leading wave is added to the initial lagging wave, as if it were also a lagging wave going from the emitter to the absorber. Negative energy and negative time add up to positive energy going forward in time. As Kramer writes, it can be assumed that the emitter generates a request wave that moves towards the absorber. Then the absorber returns a confirmation wave to the emitter, and the transaction ends with a handshake through spacetime. But this is just a chain of events from the point of view of Sudor. In reality, this is a timeless process. Everything that happens at once. If there is a special link in this chain of events, Kramer writes, it is not the link that completes the chain. This is the link at the beginning of the chain, when the emitter, having received various confirmation waves in response to its request wave, amplifies one of them, randomly selected in accordance with the rules of probability. Moreover, in such a way that this confirmation wave is embodied in reality in the form of a completed transaction. There is no word when at the end outside of the time transaction. How does this solve the main mystery of the experiment with two holes? According to the transactional interpretation, a delayed request wave propagates through both holes in the installation and initiates a leading confirmation wave from the detector screen, which passes through both holes in the installation back to the source. Each particle randomly chooses which of the proposals to accept, generating an interference pattern. But if, in a clever version of the delayed choice experiment, one of the holes closes after the particle has set off, the particle already knows about it. Because the confirmation wave has only one hole left through which it can pass back for a handshake. Kramer writes, the question of when the observer decides which version of the experiment to conduct no longer matters. The observer determined the configuration of the experimental setup and the boundary conditions, and the transaction was formed accordingly. Moreover, the fact that the registration event provides for measurement, unlike any other interaction, also does not matter anymore, so the observer does not play any special role in the process. Success in solving the mysteries of quantum physics has been achieved by adopting just one idea that would seem to contradict common sense. The idea that a part of a quantum wave can actually move backwards in time. At first glance, this sharply contradicts our intuitive ideas that the cause always precedes the events that cause. But on closer examination, it turns out that, after all, time travel, which is necessary in transactional interpretation, does not violate everyday ideas about causality. Although an out-of-time handshake occurs with the help of an advancing quantum wave moving backwards in time, this does not affect the logical structure of causality in the everyday world in any way. It should not surprise us that the way time is handled in a transactional interpretation differs from what common sense suggests. Because the effects of relativity theory are explicitly included in the transactional interpretation, the Copenhagen interpretation, on the contrary, treats time in a classical Newtonian way. And this is what underlies the contradictions that arise when trying to explain the results of quantum experiments on measuring Bell's inequality from the perspective of the Copenhagen interpretation. If the speed of light were infinite, the problems would disappear. Then there would be no difference between local and non-local descriptions of processes involving Bell's inequality, and the usual Schrödinger equation accurately described what was happening. After all, the usual Schrödinger equation, in fact, is a correct relativistic equation if the speed of light is infinite. How does a timeless handshake affect the possibility of free will? At first glance, it may seem that everything is anchored by these connections between the past and the future. Each emitted photon already knows when and where it will be absorbed. Every quantum probability wave that slips at the speed of light through the slits in the experiment with two holes already knows what kind of detector is waiting for it on the other side. We find ourselves face to face with the image of a frozen universe in which neither time nor space makes sense, and everything that ever was or ever will be simply exists. But in our time frame, decisions are made on the basis of genuine free will, without certain knowledge about their outcome. Making decisions, both human and quantum choices, such as those related to the disintegration of the atom, forming the timeless reality of the microscopic world, takes time in the macroscopic world. Kramer insists that his interpretation does not make any predictions other than those of traditional quantum mechanics, and is proposed as a conceptual model that could, in principle, help people clearly understand what is happening in the quantum world. This is a tool that is likely to be especially useful for forming intuitive ideas and understanding mysterious quantum phenomena without it. But we should not assume that the transactional interpretation is weaker in this respect than other interpretations, since none of them is anything more than a conceptual model that helps us understand quantum phenomena, and they all make exactly the same predictions. That's the point. All consolations are equally good and they are all equally bad. This, at least, means that you are free to choose which of them is the most comfortable for you, and not pay attention to the rest. Over the past 90 years, many scientific minds have been trying to comprehend the meaning of quantum mechanics. The 6 possible consolations I have described here are the best ideas they have been able to offer during this time. And all of them can be formulated very briefly. The first, the world doesn't exist if you don't look at it. The second, the motion of the particles is controlled by an invisible wave, but the particles do not affect the wave. Third, everything that could at least in principle happen happens in one of the many parallel realities. Fourth, everything that could have happened at least in principle has already happened, and we noticed only part of it. Fifth, everything affects everything else instantly, as if space did not exist. Sixth, the future influences the past. In The Nature of Physical Laws, Richard Feynman wrote, "I think I can safely say that no one understands quantum mechanics." If you can, do not torment yourself with the question, "But how can this be?" Because otherwise you will come to a dead end, from which no one has yet got out. No one knows how this can be.